Hey everyone. So it's about 7 p.m. now, so I'm going to kick things off. Today we're going to be talking about how we can use Z3, which is a really powerful constraint solver from Microsoft, to actually automatically solve and prove a lot of theorems for us. So before we get too far ahead of ourselves here, though, I do want to add a quick disclaimer that Z3 is a really complicated topic, and especially because this is an introsec talk, we kind of want to be keeping things to the very basics here. So we aren't going to be talking about how Z3 works, we aren't going to be talking about the math behind Z3, we're just going to be talking about the very basic idea of how you can use this library yourself to hopefully solve some interesting challenges. So as I talked about a little bit before, Z3 is a theorem prover. So that's going to allow us to take some theorem, some logical formula, and it's going to be able to prove that. It's either going to be able to prove that it is not satisfiable, or it is going to prove that it is satisfiable and then give us a concrete solution to it. And when I say satisfiable, what I mean by that is that this theorem, this logical formula, is actually something that you can come up with an answer. You can come up with these concrete values for each of these variables, such that that theorem holds true, such that formula is true. And so Z3, as I've mentioned here, that's used as a theorem prover, but we're talking about security here. So kind of this raises the question of why do we as security researchers necessarily care about this theorem prover? We aren't trying to solve theorems in this club so much, but what we are trying to do is we're trying to find bugs. We're trying to solve crack-me's and other reverse engineering challenges, and so something like Z3 actually saves us a lot of time in CTFs. It's a really powerful tool, and I think any reverse engineer's tool belt would be incomplete without a theorem solver like Z3. And then also a theorem solver, God, I can't talk, is actually the founding, like the basis for a lot of other really advanced tools. So one of the big ones that we're actually going to be talking about a little bit on Friday is called symbolic execution, and that will allow us to generate some input to reach any arbitrary point in code. And so that's a really powerful tool when we can make that work for us, and when we can use that to narrow down ways that we can patch, or that we can, for example, get to a vulnerable code path. So Z3 is what's called an SMT solver. SMT stands for Satisfiability Modulo Theory. So in general, what we're going to do here is we're going to generate some logical formula, some first-order logical formula. So if you've taken a class like Intro to Logic, or even Foundations of Computer Science, those are both classes here at RPI that talk about first-order logic, this is going to look kind of familiar to you. And then we're going to try to find some way using this SMT technique that we can come up with concrete values. We can come up with values that satisfy that formula. And Z3 is going to help us do that. So when I say things like formulas or theories in a class like Fox, or in a class like Intro to Logic, or in a lot of other introduction to formal logic courses out there, when people talk about theories, they mean like, oh, P implies Q or whatever, and they're just dealing with these booleans where you can have true or you can have false. However, the theories that we'll be dealing with will include those booleans as well. It'll include true and false, but it will also include a lot of other classes of inputs. So we can be dealing with real numbers, so that's any number that is not imaginary. We can be dealing with integers, which is the set of whole numbers. But oftentimes, what we're actually dealing with is what's called a bit vector, which, as the name would imply, is basically a vector. It's basically a list of individual bits, of individual ones or zeros. And so that's really useful, because when we're dealing with reverse engineering challenges, we often need to kind of consider the way that our CPU sees data as well, and we need to model it in a similar way. So when we're using Z3 to specifically tackle these reverse engineering challenges, we use bit vectors a whole lot. On top of that, we also have things for floating point numbers, which many of you are probably familiar with, as well as more complex data types. So you can model something like an array in Z3 as well, or even a function, because Z3 is very powerful. That being said, today we're kind of going to be limiting the scope of this talk, so we're going to be talking a lot about booleans, a lot about integers, and a lot about bit vectors. And for the most part, that will probably be enough for you to tackle most reverse engineering challenges that you'll face. So yeah, as I talked about before, SMT, this satisfiability modulo theory, that's a really powerful tool that we can use to find valid inputs for a CrackMe, to find valid inputs for a reverse engineering challenge. So for example, if you have a challenge where it's like pretending to be like a serial key checker, and you need to write a program that will generate a valid serial key, it's really easy to go in and look at what this program does, what this checker does for every byte in your input, and figure out what the reverse, or figure out what the bitwise arithmetic that it's doing, what the logic that it's using to check that is. And you can do that using the reverse engineering techniques that we talked about the other week. However, it's really annoying to have to go through by hand and reverse out every single one of those logical operations and figure out how to undo each of them so that you can take this output and you can get to a valid input. However, if you understand the algorithm, you can often model it as a Z3 script. And so you can take those operations that it does and you can add those in as constraints. So you can add those into the model, the Z3 model, and you can actually model this serial number checker, for example, as a logical formula, which can then be thrown into Z3, and Z3 can solve that for us. So in Z3, we have the concept of a data type. We have the concept of many different data types. However, the name for these data types is actually a little bit funny. In Z3, they're called sorts. So for example, we have an int sort, and that's going to represent an integer. We have a bool sort, and that's going to represent a boolean. We have a bit vec sort, and that's going to represent a bit vector. And then we have a whole lot of other more complicated data types. However, as I mentioned before, today we're kind of going to be just focusing on those three. So now that we understand what Z3 is, Z3 Pi is actually the Python implementation of Z3, or the Python interface to Z3. Z3 is a really, really powerful tool, and it can be used in many, many different languages. However, I, and I think many of us, are very comfortable with Python. And so when we're trying to write these scripts to crack these reverse engineering challenges for us, it's often easiest to just throw those together in Python very quickly. And so we're going to be focusing on the Python bindings for Z3. If you want to install these yourself, Z3 has a GitHub at Z3Prover, or you can install the Z3 solver package. If you just try to install Z3, that's actually not the right library. You do have to do Z3-solver. That being said, this pip package is actually not advertised on their website. It's not advertised on their GitHub. So this is what I use because it's very easy to install. However, your mileage may vary with it. If you have issues, you may be better off following the build instructions on their GitHub and building it yourself. So in general, when we're using Z3 or any kind of constraint solver, we're going to follow a very cookie cutter workflow here. We're going to be trying to do something where we import everything from Z3, we declare a bunch of variables, so that's going to be like x equals whatever, y equals whatever, or x is an int, y is an int, stuff like that. We're going to create that solver object, which is specific syntax in Z3, and we're going to add constraints. So that can be something like, well, x is greater than y, or x is equal to 3, or x is divisible by 7. And then we can add a bunch of different constraints until we finally have enough that we can solve this problem. And we can solve it once we've fully modeled the problem that we're trying to solve as a logical formula using these constraints. And then finally, once we've solved it, we can obtain that model. And so that model is going to give us the concrete answers of what each of these variables is, or what each of these variables can be. So for example, when we want to define a bunch of Boolean variables here, so when we're at that declare variable step, we're going to follow a syntax kind of like this. So p equals bool. Bool is a class here, so we're going to use an uppercase B, and then the name of that variable here. So in this case, we're just defining 3 variables, p, q, and r. If you'll notice here, we have a Python variable, and then we also need to tell Z3 what the name of this variable is. So this syntax looks a little bit funky because we're saying we have a variable named r, and also this Z3 variable is also named r. So this is just going to be used for Z3's internal representation. This is going to be used for interfacing with that variable from Python. So then when we create that solver, that's the next step, if we remember from the previous slide what the general kind of cookie cutter format was going to be. We do that very simply with initializing the solver class, which is just Z3 syntax. And that solver class is going to be the main class that's going to handle the logic of actually solving that SMT problem and doing the math to figure out what values we can have for p, q, and r, what values we can have for all of our variables. And then finally, we want to be adding a bunch of different constraints. So right here, this is the Z3 syntax for adding like an implication. So if we add to that solver, if we add a constraint to that solver with s.add, we can add an implication here. So p implies q. We can also add a lot of different constraints at once. So for example, here we're saying r is equal to the opposite of q. R is equal to not q. And we're also, in that same line, adding a second constraint. We're adding that either p is not true or r is true, or both. We're adding a logical OR constraint here as well. And then finally, the last step here is we want to check to see if this model is solvable. We want to check to see if there's any combination of variables that can make this logical formula true. And then if there is, we want to obtain those variables. We want to obtain those values. So how we actually obtain those values is a little bit interesting. So we know S is what we've defined our solver class to be here, and that's just kind of standard practice. That's just kind of how a lot of people like to define their solvers, with that S variable. And then we can just reference that with s.model like we did before here. And so then if we want to print out a specific variable, we can index into that kind of like we would in a dictionary in Python. And we can print out values that way. There are multiple ways of doing that. So we can also print out the m.eval. That's going to be the same thing. It's just slightly more explicit what you're trying to do here. So this is a little bit more concise. This is a little bit more explicit. They both do the same thing. And then the last thing is sometimes you can have a variable that isn't constrained. So if you have a model that has a lot of different variables, and one of those variables can be anything, then that's going to be kind of like a free variable, if you will, to borrow a term from the broader mathematical community. And so if we want to print out a value for an unconstrained variable, if we want to be able to just get some concrete variable, some concrete value, we can add in that model completion argument as well, and that's going to tell us that no, actually we do need this to be a concrete value. And so we need to use that eval syntax in that case when we need to pass in a little bit more information. The next thing is integers. Booleans are really, really easy. As you saw before, we have a lot of different types of kind of facts that we can add, a lot of different constraints that we can add to Booleans. Integers, pretty much the same thing, except the facts that we know about integers, as you might expect, are things like addition and multiplication and division and comparison, so if one integer is greater than the other. But the general idea is going to be really, really similar here. So we're doing the same exact thing where we define a bunch of variables here. We have x, y, and z. We do the same thing where we have a Python variable, and then we also have this string to indicate to z3 what this variable is, and kind of give it a unique identifier so z3 knows what we're talking about as well. And when we print out that model, we can have a label for that value, which makes sense to us. We are going to have to initialize a solver as well, and then we can start adding constraints. We can start getting to the interesting stuff here. And so in this case, what we're constraining is just that x squared plus y squared is equal to z squared, and also that every integer here, every number here, is greater than 0. So this is kind of that that a squared plus b squared equals c squared identity that many of you are familiar with. And then the rest of this is the same. The rest of this, we're just checking that model, we're fetching that model, and then we do the same exact thing where we then print out the variables in that model. Interestingly, when we're dealing with these integers though, when we do this, we aren't going to get a Python integer. So if you try to get something, if you try to do like m.eval x, and you try to multiply that by 2 without the is long, then Python's going to throw an error, because you're not trying to square an integer, you're not trying to square a number, you're trying to square some z3 data type here, some symbolic variable. And that kind of brings us to this next note that I want to talk about here, which is what a symbolic variable is and how we can get those. So for example here, we're adding this constraint, r is equal to not q. That's a symbolic expression. We don't have concrete variables. We don't have r is equal to 3, q is equal to false. We don't have anything like that. This is just a kind of an abstract idea that r is not equal to q. So back here we have a z3 variable that's kind of abstract, that's symbolic, that's not a concrete variable yet. And then if you try to use that as a concrete variable, so right here we've added this constraint that r is equal to not q. However, if you try to treat that like a Boolean, if you try to treat that like a concrete value, like if you try to compare, like if you try to say r is equal to not q, like if you try to check if r is equal to not q, then that's going to throw an error as well, because that's not going to return a Boolean, that's going to return this symbolic value. It's a symbolic expression, I guess I should say. And then also, not every Python, like not all Python syntax carries over to Z3. So we can see up here, we're able to say, yeah, r is exactly equal to not q. And that's a nice, convenient way of doing it. However, in Python, when you want to combine expressions, you can use the and keyword, or the or keyword, or the not keyword to indicate that you want to invert an expression. However, you can't do that in Z3. So if you try to add the constraint that not r and q here, so not r, so r is false and q is true, that's not going to work out. That's going to cause some errors for you, because once again, r is not a concrete value. R is a symbolic variable, and so you can't use these Python expressions on symbolic variables all the time. And then the last data type that we want to talk about is that of a bit vector here. We talked a lot about how computers essentially have an array of bits. They have 64 bits for a register, or 32 bits for a register if you're dealing with a 32-bit system. And so when we try to multiply numbers, for example, we can get into situations where we have an integer overflow, and where the behavior of like a Python integer versus two registers being multiplied together is actually very different. So for example, if you have really big numbers and you multiply them together and that ends up being more than 2 to the 64, then it's going to wrap around and you're going to get a different value than what you're expecting. And so when we want to replicate that, when we want to be able to kind of constrain our Z3 models to what's actually being executed on the CPU, we need to be able to kind of model the CPU's behavior as well. And so that's where bit vectors come in, because we can model a bit vector with 64 bits or 32 bits, and that's going to be equivalent to a register in a lot of ways. And so when we have these arithmetic operations, like when we try to multiply two giant numbers together, we aren't going to run into issues where that gets truncated or that wraps around, because the bit vector that we have will actually mimic the same exact behavior as a 64 or 32-bit register. And so that's going to match what the program that we're trying to reverse engineer will execute as well, and what it will get. Another thing to note here is that a lot of these operations are signed. So for example, when you do a comparison, like if you check to see if a symbolic variable is less than or greater than a concrete value, that's going to be a signed comparison. There are ways that you can do unsigned comparisons. They're just a little bit messier. So if you remembered before, we talked about how Z3 overrode some Python operators. That less than and greater than sign is one of those. However, it will default to a signed comparison, and we need to use that ULT to do, for example, an unsigned less than operation. Kind of by that same token, it will default to an arithmetic shift, not necessarily a logical shift. And so when we want to mimic specifically like an instruction that will do like a logical shift, like a logical right shift or a logical left shift, we have to use a syntax like this to mimic that, instead of doing an arithmetic shift if we want to do a logical shift. And there are a lot of other ways that we can mimic the behavior of doing unsigned or signed comparisons or division or anything like that, but it will default to signed in most cases. And then lastly, the last thing that I want to talk about here is how we actually make these bit vectors. So every time up until now, when we define one of these Z3 variables, we have a Python variable, we set it equal to the data type, and then we give it an identifier. However, with a bit vector, we need a little bit more information, because we need to know how many bits long it is. So right here, we're saying, here's a bit vector, we call it B, and it's 64 bits long, so it's going to be mimicking a 64-bit register. However, as we've kind of alluded to a couple of times here, there are a lot of issues that you can run into when you're dealing with these bit vectors. So for example, in this little code snippet, we have an 8-bit bit vector. So it's going to be a vector with 8 bits, and then we're going to add a constraint that a squared is 289. Now, 2 to the 8th, so if we have 1 byte, the biggest value that we can store there is actually going to be 256. So we're going to run into an issue here where 289 is greater than 256, and so we're going to wrap around. And so what we end up doing is we get 289 mod 256, because that's the biggest value that we can store in this bit vector, and that's going to give us 33 for that value. And so we're actually going to get the wrong value when we try to execute this code, because we'll be finding the square root of 33 instead of 289. And so that's going to lead to a lot of issues if we're not careful. And then also there are some other weird things where Python doesn't override certain operators that you might expect to with symbolic variables, so you can't add these two bit vectors, which can cause issues. However, jumping back to this, this code example, I want to walk you through one solution. And that is basically just to add a constraint here so that you can't end up with a value greater than 256. You can't wrap around. You can't have anything greater than 8 ones in your bit vector. And that will allow us to constrain this properly without overflowing that integer, and getting that square root of 33 instead. And so that's a really quick way of doing it. There are potentially more efficient ways. This is a clean way. But if you're super concerned about efficiency, I guess you can do like an unsigned comparison. That will add a tiny bit more efficiency. And then there's another really cool solution as well, and that is using that extract keyword here, that extract function. That's basically going to extract bits from a bit vector. So it's going to extract starting at the low bit here, at the low bit index, and going all the way up to that high bit index. So if we want to extract 8 bits here, so if we want to essentially cast this to a byte or a character, we're taking all of the bits between 0 and 7 and extracting those. And then we can sign extend those, and we can 0 extend those. So we're basically saying we care about these 8 bits, but we are expanding that, we're padding that out to a 64-bit bit vector here. So we're going to end up with the first 8 bits matching that bit vector, and then the others are all 0. And that's a way that we can constrain that all of those higher bits are always going to be 0. We can't have a 1 anywhere in there that we would get if there was an integer overflow. So if that integer tried to wrap around because it was too large. And there's just some other syntax of how to do this as well. So as we've talked about a lot so far, there's so many different types of variables that we can represent in Z3. However, the main ones that we're going to care about here are ints, booleans, and bit vectors. And so now that we've kind of shown you how all 3 of those types work, how all 3 of those sorts work, if you will, I want to dive into an example real quick. And this is an actual example from an actual CTF that we played in a while ago. So this is a Java program. It takes an input string and then it hashes it. Well, it hashes it. It's not a proper hashing algorithm that you would see in the real world necessarily, but it is a good CTF challenge. And then it takes that hash and it compares it to a constant. And if it matches, then that means we did this right and we get a flag. However, if it doesn't match, then that's going to be a failure condition. So when we're trying to model this as a Z3 problem, we're effectively going to be constraining that hash algorithm, and we're going to be constraining that constant that we're comparing to, because at the end of the day, we want to get that constant, and the way that we do that is by doing a bunch of arithmetic and a bunch of logic on our input to get to that constant. And so we want to constrain that after doing that, that logic, that arithmetic, we will get to a constant effectively. So here is the code for that challenge. It was a Java challenge where we have this constant here, and then we have this loop which will effectively go through, it will do some arithmetic on every element in an array, and then at the end of all of that, it's going to have some number, and it's going to spit that back at us. So it'll be taking a running sum here, a running product, multiplying that by this constant 31, and then adding the index that we're dealing with, or the character that we're dealing with, my bad. So our Z3 solution here, actually I'm just going to hop over to this window where I think it's a little bit clearer to see what's going on than on the slide. In this solution, we are, as we talked about before, we're importing Z3. We're adding a bunch of like data here, a bunch of variables, as we talked about being kind of the second step. So we're adding a bunch of variables. So we have this array of Z3 integers, as well as some Python variables here. And then we have these constants that we've extracted. So this N2, I'm sure looks very familiar. And we go through and we're just accumulating that sum there. And then finally, we're going in, we're adding a ton of constraints here. So we're constraining that every value that we get here, every final variable that we're dealing with, has to be in the ASCII range between a lowercase a and a lowercase z. And then finally, once we have all of that out of the way, we check to see if this model is satisfiable. So if it's not satisfiable, so this is just a way to check to see if there exists some set of variables, some set of values which can be slapped together to make all of this true. If not, we quit and give up, but if there is, then we're going to go through every variable and we're going to print out what it is. And so because we have this list of Z3 variables, of integers actually, we're going to be taking those integers, we're going to be converting them into characters, and then we're going to be combining all of those into a string which we can print out. So if we run that very quickly, then we can see that we do actually get a valid string here. We do actually get a valid result when we solve all of these symbolic variables, all of these constraints. So a couple of things to note about this script. We are using those ints instead of bit vectors. Basically, that's just an efficiency thing. For whatever reason, it was a lot more efficient to use integers, so Z3 was able to crunch the numbers much more quickly. And so because of that, our code is a little bit messier, and we have to account for integer overflows as well. If we use bit vectors, we could probably do this a little bit more cleanly, but it would just take longer to run. And then the other thing to note here is if we open this back up, we have this wanted length, and we're basically going to be looping through all the numbers up until that wanted length. That length is going to be the length of our string, and in this case, that was just kind of achieved by guessing. We could do that automatically by effectively just having a for loop or something like that to check every possible combination until we get a satisfiable result. But in this case, because this was a fairly simple challenge, it was actually possible to just guess that and just keep guessing and increasing that count until we got a value that would give us a nice clean answer. And then the last thing I want to say is this is a really, really cool topic. However, it is one of those topics that makes a lot more sense if you just do it yourself. So we've actually made a bunch of challenges. We've included a bunch of challenges on the tools.rpis.ec website, and we've even provided some solutions as well. So if you want to practice this, I highly encourage you to go to our tools.rpis.ec website and download that tarball of Z3 challenges and see if you can work through those and kind of put your skills to the test there. And then also there are a lot of other interesting and useful sorts and a lot of other interesting and useful data types. However, because this is an introsec meeting and because we kind of want to be moving quickly here, we don't want to get bogged down, I don't think we'll actually be going over those today. So I think this is a great stopping point. I think if you're interested in learning more, I highly encourage you to go to our website and try it for yourself. And then if you would like to ask questions, you can join our Slack. It's at rpisec.slack.com, and we would be happy to answer those. I will see you all later then.